Okay, so section 20.5. We're going to look at the relationship between the free energy, standard free energy, the standard cell potential, and the equilibrium constant. These three quantities are all related to each other. So in a spontaneous reaction, the standard free energy is negative. That's what tells us it's spontaneous. The standard cell potential will be positive, and the equilibrium constant will be greater than 1. In a non-spontaneous redox reaction, those are opposite. And so we've got this triangular relationship here, and we're going to look at the relationship between each of these pairs of things. Okay, so let's look at free energy and standard cell potential. So potential difference is the potential energy difference per unit charge. And the potential energy difference is the maximum work. So maximum work per unit charge. So E equals maximum work divided by Q. The maximum work done by the system, then, rearranging this equation, is W max equals negative Q times the standard cell potential. So the amount of charge that flows in an electrochemical reaction is quantified using Faraday's constant, which is symbolized with F. This is the charge in coulombs of 1 mole of electrons. And so 1 mole of electrons has a charge of 96,485 coulombs. So if we want to know the total charge that flows in a chemical reaction, it will be the number of moles of electrons times Faraday's constant. That will give us the charge in coulombs. And we would get this number of moles from the balanced chemical equation. So then we can substitute into our previous relationship here, where maximum work is equal to negative Q times the standard cell potential. Now we determined that Q was equal to NF, so we can put that in here. So this is negative NF standard cell potential. The standard free energy for a chemical reaction is the maximum amount of work that can be done. And so W max is delta G0. So here we get this relationship that the standard free energy change is equal to negative NF standard cell potential. F is Faraday's constant, N is the number of moles of electrons transferred in the balanced chemical equation. I can't see the chat window right now, so if you have a question, unmute yourself and ask. So let's practice this. Use tabulated electrode potentials. It says see next slide, but I think I stuck them here. To calculate delta G for this reaction, is the reaction spontaneous? So the relationship we just learned is that delta G0 is equal to negative NF E cell 0. So to calculate delta G, we need to know what E cell 0 standard cell potential is. So we need to look at the two half reactions that are occurring here. So I've got 2 sodium going to 2 sodium ions plus 2 electrons. And the other half reaction is 2H2O going to H2 Oops, I'm going to need some electrons in there. 2H2 plus 2OH minus, and this is going to have 2 electrons in it. I'm going to look for the reaction for sodium, and so there it is. So the reduction half reaction, sodium plus an electron, has a potential of negative 2.71 volts. But this is the oxidation. And so the method that makes sense to me is when I write it as the opposite kind of reaction, I change the sign. So this is 2.71 volts for that half reaction. And this H2O to H2 reaction is right here. 2H2O plus 2 electrons going to H2 plus 2 OH minus, and that is minus 0.83. So I'm going to add those together. I get 2.71 plus negative 0.83 is 1.88 volts. So that's my standard cell potential. That goes in here.
Why was it positive? For the first one, I thought it was supposed to be negative.
Okay, so this one, this reaction is written backwards compared to the one over here.
Oh, okay, yeah. So when you switch the directions, you have to switch the...
Yeah.
Okay. Which way to enter?
That's what makes more sense to me, and so that's the method I'm going to be using instead of identifying the cathode and the anode and then subtracting. That makes no sense to me. So that's why that's positive instead of negative. So I've got E cell, and then I need to figure out what N is. N is the number of moles of electrons. And if we just look at the Bound's chemical equation here, it's not obvious how many moles of electrons there are. But when we look at the half reactions, we see that it's 2 moles of electrons. So N equals 2. So here we have negative this is 2 moles of electrons times Faraday's constant, which is 96,800 and, oh gosh, 35? I can never remember that one. Can somebody help me out there? Oops. Can anybody tell me the value of Faraday's constant?
96,485.
485, thank you. Coulombs per mole of electrons. Times the standard cell potential, 1.88 volts. And I've left myself nowhere to write the answer. I'll squeeze it in here. I'll make it blue. So negative 2 times 96,485 times 1.88 is negative 36. I'm just going to round it a little bit here. 3,000. The moles of electrons cancel, and we end up with a unit here of coulombs times volt. Let's see if that's anywhere convenient. I have a hard time remembering these units because I don't use them very often. I think that's a volt is a joule per coulomb. Let me see. And my slides are messed up. I can't just zip back like I usually can, so that sucks.
Are you speaking about for volts in this case?
Pardon me?
Are you speaking about the alternative?
Yeah, volts. I think volts is equal to joules per coulomb.
I'm looking now and I see it says, yeah, joules per coulomb.
Okay, thank you. So volt is joules per coulomb, and so if we write joules per coulomb in there, the coulombs cancel out and we get joules. And so this would be negative 363 kilojoules for our free energy change. Is that spontaneous?
Yes.
Yeah, it's negative, so it's spontaneous. Oh, shoot. Come on. Well, I guess I never put the answer in that one. Oh well. Here's a conceptual question. Considering the result of experiment 20 points of example 20.6, and that's in the textbook. We don't actually have to know what that was because it's telling us the conclusion right here anyway. The calculation revealed that the reaction is not spontaneous. That's not the one we just did. Based on conceptual reasoning, which of the following best explains why I2 does not oxidize Br minus? So we've got three choices here. Bromine is more electronegative than I, therefore you don't expect Br minus to give an electron to I2. I is more electronegative than Br, therefore you do not expect I2 to give an electron to Br minus. Or Br minus is in solution and I2 is a solid. Solids do not gain electrons from substances in solutions. Hopefully we recognize that last one as being ridiculous, because solid electrodes do gain and lose electrons to things in solution. So which is more electronegative, bromine or iodine?
Bromine.
Yeah, bromine. Bromine because bromine is above iodine on the periodic table. So bromine's more electronegative than iodine. So bromine is more attractive to the electrons. And so here bromine has the electron, and in order for this reaction to happen, it has to give it to iodine. Iodine is not as attractive to the electrons, and so that's not going to happen. So that's the answer. Okay, so let's look at the relationship between standard cell potential and the equilibrium constant. So we learned that the standard free energy change is equal to negative RT natural log of K. That was from chapter 19. And we just learned that the standard free energy change is equal to minus NF standard cell potential. And so if both of these equal delta G0, then these two things must be equal to each other. So we've got these guys. And then we need to rearrange this and solve for the standard cell potential. So I'm going to multiply both sides by -1 to get rid of the negative sign. And then I'm going to divide by NF on both sides, and that gets rid of those. Now we've got this kind of a mess here of, we have three, the temperature is often a constant, and then we've got the gas constant, and we've got Faraday's constant. And for whatever reason, electrochemists like the base 10 log and not the natural logarithm. And so if we look at all of these relationships here, here's the value of the gas constant, here's the temperature at standard is 298.15 Kelvin, and the value of Faraday's constant, and then to convert natural log to base 10 log, we multiply by 2.303. If you combine all those things together, what you end up with is that E cell equals negative, is it negative? Oh, no, I'm blanking. I'll leave the negative off for now. 0.0592 volts over N times the base 10 log of K. Yeah, that's right. Oh, yeah. It's down here too. It's been a long day. Any questions?
Yeah, you said that you would convert the ln to natural to just the regular log, and so you times that by the 2.303.
Yeah.
Okay, cool. I was just making sure.
Yeah. And that's not something that I think you need to know, but a lot of you are curious about, well, how does this just change from natural log to base 10 log? You can't just change it willy-nilly. You have to actually do a conversion. But the conversion is in here. And so we take all these messy numbers and we lump them in here as 0.0592 volts. Oops, not what I meant to do. Oh, good grief. Okay, let's practice with this one. Use the tabulated electrode potentials to calculate K for the oxidation of iron by H+. So it says see slide 62, but I rearranged things, and so it's actually over here. So iron to iron 3. So that's this one right here, iron 3 to iron. So that is minus 0.036. And the hydrogen ion to hydrogen gas, that's the standard hydrogen electrode, and that one's 0. So if we look up these half reactions, here we've got 2 iron going to 2 Fe 3 plus 6 electrons. As a reduction, that's negative 0.036 volts. But here it's an oxidation, and so I'm changing the sign. So it's positive. The other half reaction, 6H plus 6 electrons going to 3H2, that's the one that we decided to use as 0. So our standard cell potential here is positive 0.036 volts. We need that so that we can use our equation. So we just learned that the standard cell potential is equal to 0.0592 volts divided by N times the log of K. we need to identify what N is. N is the number of electrons, moles of electrons. And so here in the balanced chemical equation here, it's 6. So I'm going to do the rest of this on my calculator. I've got 0.036 times 6 divided by 0.0592. So I've got the base, the log of k is equal to 3.6486. So k equals 10 to that. Or 4452. So that's probably going to be 4.4 times 10 to the 3. Any questions? Four 4.5 times 10 to the third. I think maybe yeah, I didn't round. 4452 should have rounded up to 4.5. Okay, so this slide gives us a summary of the relationships we've looked at here. So between standard cell potential and standard free energy change, delta G0 equals minus NF E cell. Between delta G and K, we've got that from the previous chapter, delta G equals minus RT natural log of K, and the relationship between standard cell potential and the equilibrium constant. So, a conceptual question. A redox reaction has an equilibrium constant of 1.2 times 10 to the 3. Which statement is true regarding delta G and E for this reaction? Well, we don't have to do a calculation, but we kind of have to look at the relationships here. So they're telling us that K is a large number. So if I put a large number in here and I get a logarithm of a large number, is that going to be positive or negative? It's going to be positive. Yeah. So large K here means that the standard cell potential is going to be positive. So we can eliminate two of these choices then, where standard cell potential is 0. And then we can look at this relationship with delta G. Here we've got negative RT natural log of K. Again, K is a large number, and so the natural logarithm of a large number is also positive. And so these other two numbers, R and T, are positive, right? And so this negative sign means that delta G must be negative. So this must be the answer.